Multi-class classification evaluation. The classification metrics that we have addressed so far are for binary classification problems in which we only have two classes. But what if we had multi-class classification problems in which there are multiple and not just two classes? The multi-class classification evaluation is just an extension of the binary case. So that means that you could, for each class, you could consider your evaluation as that class, particular class versus the rest for each of the classes. So it's going to be a collection of true versus predicted binary outcomes, one for each class. Confusion matrices are especially useful for multi-class evaluation, as we are going to see an example. Also, you can use the classification report generated by Scikit-Learn for multi-class classification problems. Overall, for multi-class classification problem, the evaluation metrics are just an averaging of across different classes, but we can actually have different ways to find that average. There are the macro averaging approach and the micro averaging approach. So let's see how macro averaging and micro averaging work for multi-class classification. Let's see an example of a multi-class classification problems. If you remember the fruit classification problem that we had a set of fruits, different fruits such as oranges, lemons, and apples. So suppose that we have run a classification on this problem, and this table shows the result. This is just a few instances of the result, as you see here. In the first column shows the original class, and the second column shows our predicted result from our algorithm, and the last column shows whether our prediction is correct or not. So if we want to find the average, the macro averaging, first of all, how does the macro averaging work here? How should we find the average here? In macro averaging, each class has equal weight, no matter how many number of instances do we have in that for that class. For example, here you can see that for oranges, we actually have 1, 2, 3, 4, 5 instances. And for lemon, we have 2 instances, and for apple, we have 2 instances as well. Although they have different number of instances, they have different sizes, but each class in macro averaging gets equal weight. So how to compute macro averaging? The first step is to compute metric within each class. So for example, we're going to compute the average of correct prediction, the precision for oranges, then for the lemons, then for the apple. Second step is to average across the classes that we have. So let's see how does it work for this example. So for example, for the orange class, we have 5 instances. Out of the 5 instances, only 1 instance we have correct prediction. So the averaging for this, the precision for this class is 1/5 or 20%. For the lemon class, we have these 2 instances, and one of the instances we have made the correct prediction, so that the precision is 1/2 or 50%. For the apple class, we have 2 instances, and both of our instances we have made the correct prediction, so that means that our precision is 2/2, which is 100%. So now we actually find the macro average over these results. So the macro averaging would be 20%, the precision for the first class, plus the precision for the second class, 50%, plus the precision for the third class, apple. So that's, and they get equal weight, although we have 5 instances of oranges, we have 2 instances of lemon, and we have 2 instances of apples. But as you see here, all of these classes, they get 1, the equal weight here. So we add the precision values up and then divide them by the number of classes that we have, which are 3. So the macro averaging would be summation of the precision scores divided by 3, which is 57%. So that's the macro averaging score for this classification problem. Now let's see how micro-averaging works. We're going to work on the same classification problem, the fruit classification problem. In micro-averaging, instead of each class, that was the case in macro-averaging, each instance has equal weight. And this is going to make the largest class, that means the class with the largest number of instances, to have the highest influence. Let's see how the micro-averaging process works. The first step is to aggregate outcomes across all classes. What does this mean? So we have 5 classes of orange here, 5 instances of class orange, 2 instances of class lemon, and 2 instances of apple. That means we have total 9 of instances here. And out of these 9 instances, we have 1 class here. For orange, 1 instance has been predicted correctly. 1 instance for lemon and 2 instances for apple has been predicted correctly. So that's a total of 4. And that means 4 out of 9 have been predicted correctly, the precision score for that. So we're just going to compute the metric with the aggregated results. We're going to do it here for precision, but you can actually do it for other metrics as well. So the precision here, or the micro-averaging precision score, would be 4 corrected prediction divided by the number of instances, the total number of instances, which is 9. So that's 4 divided by 9, which is 44%. So the micro-average precision for this multi-class classification problem is 44%. Let's see how macro-averaging and micro-averaging are different and when should we use which one. If the classes have about the same number of instances in your problem, macro and micro averages will be almost the same. On the other hand, if in your data sets, some of your classes are much larger than others, that means there are more instances of particular classes, and if you want to weight your metric toward the largest class, then use the micro averaging. If you want to weight your metric toward the smallest ones, then use the macro averaging. If the micro average is much lower than the macro average, that means it's smaller, then examine the larger classes for poor metric performance. Find the classes that have the largest number of instances, and then investigate those for the reason for poor performance. On the other hand, if the macro average is much smaller than the macro average, then examine the classes, the smaller classes, the classes with the smaller number of instances for poor metric performance. Confusion metrics for multi-class classification problems. Let's see an example for a confusion matrix for a multi-class classification problem, which here is the digit data. So the digit data, there are 10 classes of data, and that's class 0, class 1, class 2, up to class 9. So the confusion matrix for this problem would be a 10 by 10 confusion matrix. We have run the SVC classification model with linear kernel and with the RBF kernel. Here is the confusion matrix for the classification problem using the SVC linear kernel. The accuracy score is 97%. And in this confusion matrix, you can see the true labels here and the predicted labels here. The numbers in this table shows the number of instances that being classified for such the label. For example, the 37 for row 0 and column 0, it shows that 37 instances have been correctly classified as 0, and 42 instances have been correctly classified as digit 1, etc., etc. So for example, there is a 3 here, which is for label 8, The true label is 8, but it has been predicted as or labeled as 1. So there is a misclassification error here. And also this is a heat map. As you can see, the darker the color of a cell, it shows the more accurate or the weight of that class. So for example, as you can see here, we have 51 instances of digit 6 has been correctly classified as label 6. Now let's take a look at the SVC with the RBF kernel for this problem. The accuracy score here is much lower, is about 49% almost. And as you can see, the SVC with RBF kernel has a strange actually problem with labeling the numbers as the wrong label of 4. So as you can see, for this column 4, so almost every data point has been, a lot of data points have been incorrectly labeled as digit 4. So it seems that this SVC kernel has a problem with digit 4.